Everyone, we're Senior Design Group 12. I'm Jeremy Murphy. It's Fang Zhao Cheng over on the right, and George Rufeus. Our advisors are Dr. To and Dr. Gripperman, and the title of our project is Biomimetic Design of Phononic Structure for Impact Resistance Continued Study. Now, biological hierarchical structures are found all throughout nature. This figure gives a few examples, such as a lobster claw, deep sea sponge, as well as in human tooth enamel. These structures consist of structures within structures that have been scientifically proven to have toughness, but the question is, are they impact resistant? If so, they could have a wide range of applications in structural and safety technologies.
In the previous semester, Dr. To developed 3 distinct hierarchies to be modeled on the macroscopic level. These hierarchies were developed using MATLAB script. The previous design group used 3 test methods and used an ultrasonic sensor as an output. However, those tests were deemed to be unrepeatable because the ultrasonic sensor had to be removed and replaced after each test round.
So these are the 3 different hierarchies we have. Each of them has the constant number of steel and the acrylic discs. As shown in the graphs, the white ones are steel and the black ones are acrylic. The resistance are increasing from the hierarchy 1 to hierarchy 3 by increasing the number of patterns. We achieve this by adding more acrylics in regular intervals. We also use ultrasonic gel to remove the space between these discs and increase the transmittance.
Our primary objective was to develop a repeatable test input. This means that if after each test run there would be very little variance. And also we wanted the apparatus to be easily removed and placed in new environments. In addition, we wanted a more permanent output sensor, one that we could physically attach to the test apparatus itself. This sensor would be measuring along the frequency domain to locate band gaps, which are areas along the domain in which transmittance falls to 0.
So for the sensor, we choose piezoelectric sensor because it is cheap, simple, and can be permanently mounted on a device. Our band gap frequency is around 40 kHz, and the resonant frequency of our sensor is around 215 kHz, which seems to be a little bit far away from our band gap. However, that is the closest resonant frequency we can get so far. Before performing tests on 3 different hierarchies, we also attach it to the aluminum block for testing its functionality.
Now, for choosing an impact method, as mentioned previously, the group from last semester used 3 different methods. The issue with these were they either lacked the frequency content to compare to the theoretical model, or they lacked the power to transmit through the large sample we have here. The steel ball drop was determined by this group to be the most promising, and therefore our impact method has been modeled off of that. When we ran the tests on the aluminum block, we discovered that there was a lot of high-frequency noise, which we accounted for by running it through a low-pass filter. The data was captured in MATLAB through a DAC unit, as shown in the figure above, and that left us with a lot of 60 Hz noise. We decided not to filter the 60 Hz noise out using a high-pass filter because it may interfere with the low frequencies which were present in large amounts in our input signal.
Our impactor is a hemisphered steel rod. The reason why we chose to use a hemisphered edge is to maximize the amount of force transmitted over a smaller surface area without penetrating the top steel discs. We wanted it to be a more massive disc so that there would be enough power and force to transmit along the entire apparatus. In addition, we use a PVC pipe as a track to make sure that this steel rod would hit the steel disc at the same point run after run.
Now, we did 10 runs with each hierarchy to attempt to prove that our test is repeatable. You can see these 3 figures represent each of the different hierarchy tests in the time domain. They are on a very small order of time magnitude, up to about 0.2 seconds, and the different runs are shown in colors here. You can see that there's extremely small variation between these runs, which helps to verify our repeatable attempts, as well as the fact that each of the initial impact points are very thin, sharp impacts, which are exactly the type we were looking for and should indicate that the signals have good high-frequency content that we can compare to theory. Now, these voltage magnitudes are relatively low, about 0.4, 0.9, 0.5. The reason for that is, as Feng mentioned before, there's a degree of distance between our sensor's resonant frequency and the limitation of the DAC unit, but it's still good enough to give us a pretty decent result.
This is a theoretical model of the hierarchy 1. The red block is the DAC range, which obviously cannot reach our band gap, and we believe that is because of the equipment limitation. And as shown in the hierarchy 1 spectrum, you can see there is a counterpoint right here, and that cutoff frequency is even smaller than our DAC range, which is up to here. And we believe that is because our input signal doesn't contain high enough frequency. And the huge spikes is the 60 Hz noise we have mentioned before. It has such a big power because it is directly from the filter.
One of the main issues we had while we were testing was clipping. As you can see in the figure up here, it's represented by a flat peak rather than a sharp peak at the proper voltage. And this happens when the input voltage exceeds the input range of the sensor and is literally cut off. The other main issue is the fact that the theory shows transmittance, which is a comparison of input to output, and the figures we presented before were simply output. So in an attempt to measure the input signal, we tried different methods such as a force sensor or using the same piezoelectric. However, our piece was too massive and exceeded the input ranges for these sensors. We also attempted to use a better DAC unit, one with a much larger bandwidth. However, we had technical difficulties getting it to work with the rest of our equipment.
In conclusion, though, we can say that we do have a repeatable test, thus confirming our initial purpose. After each test run, there was very little variance between each of the runs. However, some modifications do need to be taken into consideration, one of these being the size and shape of the impactor. We felt that it ended up being too massive to trigger the input, and did actually end up breaking a couple of piezos. In addition to that, there was a lot of noise prevalent in the test results. This does have a major impact in our final test data. In addition, a better DAC unit is needed so that we can reach the very first band gap.
So, three main things we need to pay attention in the future work: the DAC unit, input signal, and output signal. The most important thing is we need to get a better DAC unit so that we can capture frequencies around our band gap. Since our input signal doesn't contain high enough frequency, we also need to modify the impact piece to create a smaller impact area. For the output signal capture, the next group can also try out different sensors to see which one works best for this project. A less noisy filter will be helpful to remove the 60 Hz noise, and additionally, we can also try to produce a method to measure input and output signal at the same time for measuring transmittance.
We have an equipment list here. Our total budget was $200, and you can see that all we had to buy was our piezoelectric disc transducers. The rest of the equipment was generously loaned to us by Dr. Vipperman. And we'd like to thank Dr. Robertson, our advisors, Heather Manns, grad students that helped us out, as well as Stemming for providing the materials, and the machine shop. Questions?
Any questions?
Yes.
For the impact piece, we're talking about how you need to modify the geometry so it break things. Is that going to be like experimental type modification, or are you going to have equations?
One of the things Dr. Toe recommended us doing for future work is to possibly, instead of having a hemisphered edge, to have more of a conical face. The reason why we initially didn't do that is when we were doing test runs using just a regular old pick to make sure that we would get some sort of signal, was it actually ended up penetrating the steel discs. So we went with a hemisphere shape so that we wouldn't, it wouldn't cause penetration and actually cause sticking, which would affect the quality of the end result.
So I think he was asking you, can you envision doing a theoretical analysis to make any predictions on what would work, since you have this difficult balance between damaging this sticking it?
We could certainly, it wouldn't be hard at all to find out what kind of power we need to transmit through the sample,
Yeah.
as well as I believe that a sort of preliminary theoretical model could be made for the type of output frequencies you would expect, but as we can see from our testing, there are a lot of variables that go into that. So as I said, it would be just preliminary, and I'd say that the most fruitful results as far as that goes would definitely come from experimentation.
Okay.
Yes?
What was the limitation on getting a higher DAC unit? Was it just cost?
It was a combination of cost and the one DAC unit that we did have accessible that could have possibly reached the frequency range, the cutoff frequency we were looking for. It was running into PC compatibility issues, in which this was a very, very old unit, and the hookups that it needed to mate with the PC, they don't exist on modern computers anymore. So we were running into that sort of issues.
Okay.
Okay, let's thank our speakers.